Dear students, myself I am Mamta Devi AB, Assistant Professor of Chemistry. In this video, I am going to explain session 53 of Radiation Chemistry. The contents of this video are explanation of comparison of radiation chemistry with photochemistry, units of radiation that is rad, gray and Rontgen, dosimeter that is Frick dosimeter. Comparison of radiation chemistry with photochemistry. In radiation chemistry, range of wavelength used is less than 200 angstrom units, whereas in photochemistry, the range of wavelength used is between 2000 to 8000 angstrom units. In radiation chemistry, energy involved is high, that is greater than 100 electron volts. Gamma rays, X-rays, alpha particles, electron beams are used. In photochemistry, energy involved is low, that is 1.2 to 12 electron volts. Visible, UV, near IR radiations are used. In radiation chemistry, radiation may or may not be monochromatic, whereas in photochemistry, radiation must be monochromatic. In radiation chemistry, ionic yield is calculated, whereas in photochemistry, quantum yield is calculated. In radiation chemistry, reaction initiated by high energy radiations like gamma, whereas in photochemistry, reaction is initiated by energy radiations like UV and visible. In radiation chemistry, the primary step is ionization, whereas in photochemistry, the primary step is excitation. In radiation chemistry, effects are more drastic and complicated, whereas in photochemistry, effects are simple. In radiation chemistry, all the species, that is, solute, solvent, impurities undergo change, whereas in photochemistry, in solutions, only the dissolved substance undergo change. In radiation chemistry, chemical dosimeters are used to measure absorbed energy, whereas in photochemistry, chemical actinometers are used to measure the absorbed energy. Units of radiation. The different units are available to denote the dose, that is, the amount of energy absorbed by unit mass of a substance. Those units are rad, gray and Rontgen. Rad, radiation absorbed dose. It is defined as the absorption of 100 ergs of energy per gram of the substance. Rad is denoted by the symbol RAD, rad. 1 rad is equal to 10 to the power of minus 5 joules per gram, that is equal to absorption of 6.24 into 10 to the power of 13 EV per gram, or 1 rad is equal to 0.01 joules per kg. Gray. Gray is defined as the absorption of 1 joule of energy in the form of ionizing radiation per kg of matter. It is the SI unit of radiation absorbed. Gray is denoted by the symbol GY. 1 gray is equal to 1 joule per kg, or 1 gray is equal to 100 rad. Rontgen. Rontgen is defined as the amount of radiation when exposed to 1 cm cube of dry air at STP, which produces ions carrying 1 ESU of either sign. It is based on the ability of radiation to ionize air, or it is a measure of ionization of the molecules in a mass of air. Rontgen is denoted by the symbol capital R. Rontgen is equal to 2.58 into 10 to the power of minus 4 coulombs per kg, or 1 Rontgen is equal to 0.87 rad, that is equal to 8.7 into 10 to the power of minus 3 gray, that is equal to 8.7 milligray. Dosimeter. Dosimeter is a device or instrument used to measure absorbed dose of ionizing radiation. Dosimetry. The technique used to measure absorbed dose of ionizing radiation, or measurement of dosage used for irradiation and calculation of yield of products formed is called dosimetry. Example, Frick dosimeter. Frick dosimeter or ferrous sulfate dosimeter. Principle: the quantity of energy absorbed induces a definite amount of chemical change which can be measured by chemical dosimetry. It is independent of both the dose rate and nature of the radiation. Frick dosimeter is based on the study of the extent of oxidation of ferrous to ferric ions induced by dose absorbed. Function of dosimeter. Dosimeter solution is prepared by dissolving 0.4 gram of more salt, that is FAS, 0.06 gram of sodium chloride and 22 cm cube of concentrated sulfuric acid in a dm cube of distilled water. A portion of this solution is exposed to gamma radiation for a certain period of time. Ferrous is oxidized to ferric ions. The rate at which ferrous gets oxidized to ferric ions can be easily followed. If a relation between rate of oxidation and radiation absorbed is known, then the amount of radiation absorbed can be calculated. The concentration of Fe3 plus ions produced, that is X, is determined spectrophotometrically at 304 nanometer by plotting concentration of Fe3 plus ions against optical density. The standard yield of Fe3 plus ions or G value is 15.5 ions per 100 eV of energy. By comparing with the standard value, the unknown dose is estimated. The sodium chloride is added to reduce or eliminate any sensitivity to organic impurities. That is, 15.5 Fe3 plus ions are produced by 100 eV of radiation. Therefore, X Fe3 plus ions are produced by 100 into X divided by 15.5 radiation. In this way, the amount of absorbed dose is measured. However, this dosimeter is used to measure low doses only. If you want to study more about these topics, please refer Essentials of Nuclear Chemistry by H.J. Arnikar, Principles of Physical Chemistry by Puri Sharma and Patania, Essentials of Radiation Chemistry by A. Majumdar. Thank you.